Okay, so we've proved now that the uniform limit of a sequence of continuous functions is continuous. Now, a concept very related to continuity is the concept of a limit as x approaches an input. Let's see how this concept interacts with the uniform limit. And what we've seen already is that it definitely does not interact well with the concept of a pointwise limit. For instance, when we studied f sub n of x equal to x to the n on 0, 1, this sequence has the property that f sub n converges to the function which is 0 when x is less than 1, 1 when x is equal to 1, pointwise. But if we try to take the limit as n goes to infinity of the limit as x approaches 1 of f sub n of x, what will we get? Well, let's evaluate it from the inside out. The limit as x approaches 1 of f sub n of x, well, f sub n of x is this, it's x to the n, which is a continuous function. So I can evaluate this limit by just plugging in x equals 1. I get 1 to the n is 1. So I'm left with the limit as n goes to infinity of 1. I'm going through this in so few words because I've said it before. What's the limit of as n approaches infinity of 1? Well, that's a constant sequence. That converges to 1. On the other hand, if I take the limit as x approaches 1 of the limit as n goes to infinity of f sub n of x, well, what do I get? Well, I know what f sub n, limit as n goes to infinity of f sub n of x is. It's this. It's the function that's 0 when x is less than 1, 1 when x is equal to 1. But, I mean, informally talking, the limit as x approaches 1 doesn't care what happens when x is equal to 1. So I need only look at what happens when x is not equal to 1. That function is 0. So the limit as x approaches 1 of 0, which is 0. Those two things are not the same. So pointwise limits can screw up limit at a limit point of the domain. Uniform limits don't, and the proof is a little bit similar. So let's suppose that f sub n from u to r is a sequence of continuous functions. Let's suppose that c is a limit point of u, and that for all n in the natural numbers n, the limit as x approaches c of f sub n of x exists. I'll give it a name. I'll call it L sub n. That's what L sub n is. Excuse me. Let's let f from u to r be the uniform limit of f sub n. I want to show that the limit as x approaches c of f of x exists, and the limit as n goes to infinity of L sub n exists, and, moreover, that these two things agree. There's what I need to prove if I want to prove this theorem 4.2.2. Well, let's do that. Step 1, well, I want to show that this limit exists. How do you show that a limit of a sequence of numbers exists? You show that this thing is a Cauchy sequence, and let's try to figure out why. So I'll go off to the side. So there's L sub n, and there is L sub m. I get to assume that n and m are both bigger than some big N, which is a number that I get to pick. Can I find some things that are close to these things? Well, I know that f sub n of x converges, so I know that the limit as x approaches c of f sub n of x is equal to L sub n. So as long as the absolute value of x minus c is less than some delta, which maybe depends on n, I can get this distance to be less than an arbitrarily small epsilon. Similarly, for the same reason, if the absolute value of x minus c is less than some delta, which depends on m, right? The choice of delta depends on what choice of m or n you're taking. If this is small, then this is less than epsilon. Where here is f sub n of x, here's f sub m of x. Nice. So, as long as I can find a single choice of x that satisfies both of these inequalities, maybe I take the min between delta n and delta m. Okay, well now I still need the difference between f sub n of x and f sub m of x to be small. Right, my eventual goal was to get this point to be close to that point, and now I've gotten both of them to be close to these points. But remember, f sub n converges uniformly to f of x. So, let's draw in blue. As long as little m is bigger than some choice of big N, and little n is bigger than some choice of big N, I can get both of those to be close to a single f of x. Alright, so now I see everything. I can get this to be less than epsilon, I get this to be less than epsilon, and I see everything that I need. Cool, so now let's just take that picture and put it into practice. I see 4 segments in this path. 1, 2, 3, 4. So if each of them has length less than epsilon over 4, I will be happy. So I'll just remember that. Alright, so let's consider any epsilon bigger than 0. Since little f is the uniform limit of f sub n, there exists some big N such that for a little n bigger than big N and all u in the set big U, the difference between f sub n of u and f of u is as small as I want, and I know how small I want. Epsilon over 4 is as small as I want. Alright, so going backwards, the last thing that we did in this argument is we got this to be close to that, this to be close to that. That's what we just wrote down. Let's explain why that means f sub n of x is close to f sub m of x. Well, that's easy enough to do. And again, this is true for every independent of input. So f sub n of u minus f sub m of u is equal to f sub n of u plus f sub n of u minus f of u plus f of u minus f sub m of u. Apparently easier done than said. I struggled with those words. And why is that the right thing to do? Well, it's because I know f of u is simultaneously close to both of these. So this is less than or equal to the absolute value of f sub n of u minus f of u plus f of u minus f sub m of u. Oh, put those absolute value bars in. Now, since I know that little m is bigger than big N, I know that this is less than epsilon over 4. Similarly, because little n is bigger than big N, I can use this to say that this difference is less than epsilon over 4. So this whole thing is less than epsilon over 4 plus epsilon over 4, which is equal to epsilon over 2. So, off here to the side, I have just explained why this length is less than epsilon over 2, as long as these were less than epsilon over 4. Alright, so now let's get those vertical segments. The limit as x approaches c of f of x is equal to L sub n. The limit as x approaches c of f sub m of x is equal to L sub m. So there exists some delta n and delta m, such that if 0 is less than absolute value of x minus c is less than delta n, then this difference is less than as something as small as I need, and I know as small as I need epsilon over 4. Sorry, didn't mean to screw up the color coding there. Similarly, if 0 is less than the absolute value of x minus c is less than delta m, then this difference is less than epsilon over 4. Whenever you see two different choices of delta and you need something that's smaller than both of those choices of delta, take them in. So I'll set delta to be the min between delta m and delta n, and assume that 0 is less than the absolute value of x minus c is less than delta. In fact, there's something that's worth pointing out. Because c is a limit point of u, such an x exists. Nice. So now I will study the difference between L sub m and L sub n. Well, I know something that will be simultaneous. I know something that will be close to L sub n and something that will be close to L sub m. F sub n of x is close to L sub n. F sub m of x is close to L sub m. So I will subtract and add those. So absolute value of L sub n of x minus L sub m of x is equal to the absolute value of L sub n minus F sub n of x plus f sub n of x minus f sub m of x plus f sub m of x minus L sub m. This is true by adding and subtracting f sub n of x and f sub m of x. Next, by the triangle inequality, that is less than or equal to absolute value of L sub n minus f sub n of x plus absolute value of f sub n of x minus f sub m of x plus the absolute value of f sub m of x minus L sub m by the triangle inequality. So now I can put together all the things that I know. I know that 0 is less than the absolute value of x minus c is less than delta. So that means 0 is less than the absolute value of x minus c is less than delta n. So this difference is less than epsilon over 4 by 4.2. Okay, there's a referencing error. By 4.2. That's less than epsilon over 4 plus f sub n of x minus f sub m of x. Well, I know that for absolutely every input u, as long as little n and little m are bigger than big N, this difference is less than epsilon over 2. But little n and little m are still bigger than big N. And finally, by reason 4.3, this one, this is less than epsilon over 4. Hey, look, it's almost as if we planned that that would add up to epsilon. So let's read through this proof and see if it's actually a proof. That L sub n is a Cauchy sequence. We started by considering any epsilon bigger than 0. Good. So for all epsilon bigger than 0, we came up with a choice of big N. So there exists some big N. We then considered any m and n bigger than big N, and concluded that the difference between L sub n and L sub m is less than epsilon. Notice that on the way we came up with this choice of delta. That was part of the proof, but not part of the conclusion. In the conclusion, I don't care about delta. Nice, so that completes that. So, L sub n is Cauchy. What do I know about Cauchy sequences of numbers? Cauchy sequences of numbers have limits. So, let's let L be the limit as n goes to infinity of L sub n. So let's go back up to the actual theorem. What were we trying to show? So, the conclusions were, the limit as x approaches c of f of x exists, the limit as n goes to infinity of L sub n exists, and they agree. So what have I checked so far? I've checked that this exists. So that means I need to show that this exists and that these two things are the same. So here's the mindset I'll take. The way that I will prove that the limit as x approaches c of f of x exists is by proving that it is equal to the limit as n goes to infinity of L sub n, since I know the limit as n goes to infinity of L sub n exists. So, erasing that. So what I want to do still is show that as x approaches c, f of x converges to the limit of these L sub n's. So it's that L will be the limit as n goes to infinity of L sub n. I will be done if I can show that the limit as x approaches c of f of x is equal to L. So let's do that. So what is it that I want to show? So I will want to show that for any epsilon bigger than 0, there exists a delta bigger than 0 such that for all x in U, if the absolute value of x minus c is less than delta, and bigger than 0, then the absolute value of f of x minus L is less than epsilon. So pictorially, I eventually want f of x and L to be close. So I'll draw dots representing those two. So let's see what I can figure out. So L is definitely close to these L sub n's. Right? L is the limit of the L sub n's. So as long as little n is big enough, I can make that small. But f is also the uniform limit of f sub n. So by taking little n big enough, I can get this to be close to f sub n of x. And notice, this is true for all x. The choice of little n does not depend at all on the choice of big X because of this uniform convergence. All right, so now fix a little n that's big enough so that both of those two things happen. Can I get f sub n of x to be close to L sub n? Yeah, of course. Because limit as x approaches c of f sub n of x is equal to L sub n. Nice, so I have 3 legs there. It looks like I'll need to divide my epsilons by 3. Let's do that. So let's let L be the limit of L sub n. Okay, I've already said that. Since f is the uniform limit of... Well, here's a problem. I should probably start this proof with something like consider any epsilon bigger than 0. As soon as I do that, then I will know that since f is the uniform limit of f sub n, there exists some big N, such that for a little n bigger than big N, this is just big N1. I see that I'll need 2 of them, because this will need a big N, that will need a big N. So there will be 2 choices of big N. There exists some big N1 such that for a little n bigger than big N1 and all u and u, the absolute value of f sub n of u minus f of u is less than epsilon over 3. The reason to divide by 3 is because the picture to the side told me I have to. Let's let L be the limit as n goes to infinity of L sub n. There exists some big N2 such that if little n is bigger than big N2, then the difference between L sub n and the limit is less than epsilon over 3. Now I need little n to be... I need both of those things to be true. So I'll need little n to be simultaneously bigger than both of those things. So I'll take n to be the max between those 2 things. Whenever you see 2 different big N's and you want to make sure both of them walk, take the max. So take big N to be the max of the 2, and little n to be bigger than big N. Since the limit as x approaches c of f sub n of x is equal to L sub n, there exists some delta bigger than 0, such that 0 is less than the absolute value of x minus c is less than delta, then the difference between f sub n of x and L sub n is less than also epsilon over 3. So notice, let's just read that on its own and see if it follows. Limit as x approaches c of f sub n of x is equal to L sub n. That's a limit statement, and I have a positive choice of epsilon specified above, so I don't need to redeclare it. So I know that there exists a positive number delta, such that if 0 is less than the absolute value of x minus c is less than this positive number delta, then the difference between f sub n of x and L sub n is less than epsilon over 3. Yeah, that's like the definition of the limit. All right. So now what'll I do? I'll consider any x and u. I'll assume that 0 is less than the absolute value of x minus c is less than delta, so that this happens. Then, the absolute value of f of x minus L, well, this picture tells me what I need to add and subtract. I want to get these 2 things to be close. I will add and subtract things that I know to be close to both of them. So this is equal to the absolute value of f of x minus f sub n of x plus f sub n of x minus L sub n plus L sub n minus L by adding and subtracting f sub n of x and L sub n. By the triangle inequality, this is less than or equal to the absolute value of f of x minus f sub n of x, absolute value, plus absolute value f sub n of x minus L sub n, plus the absolute value of L sub n minus L. And now let's just put together what we have. F sub n of x minus f of x, that's small by 4.4 because little n is bigger than big N. So by 4.4, that first piece is less than epsilon over 3. By 4.6, f sub n of x minus L sub n is less than epsilon over 3 because I know that 0 is less than the absolute value of x minus c is less than delta. By 4.5, the difference between L sub n and L is less than epsilon over 3. So I can replace this L sub n minus L by epsilon over 3. And it's almost like I planned that this would add up to epsilon. So that got a little bit complicated. Let's read through step 2 and see if it actually does what I need. So apparently I didn't actually start with let epsilon be bigger than 0, but let's consider any epsilon bigger than 0. Let's let epsilon bigger than 0. I now need to come up with a choice of delta. So what do I do first? I come up with a choice of big N1, a choice of big N2, and a choice of big N. Notice that's part of the proof, but not part of the conclusion. But I kind of needed to come up with a choice of big N because I only know that f sub n is... I only know the limit of... I only know things about the limit of f sub n of x, so I need f sub n to come up with my delta. We came up with a delta anyway. There it is. We then considered anything in the domain with 0 or less than the absolute value of x minus c is less than delta, and concluded that the absolute value of f of x minus l is less than epsilon. Yeah, that's exactly what it means by the limit as x goes to c of f of x to be equal to l. But l is just what we called the limit as n goes to infinity of l sub n. So we are done. So I'll come back in a moment. We'll recall the questions that we asked in the previous section. We'll come back to them and we'll settle them. We'll just determine their answers. Cool. See you in a moment.